We've been talking about continuity for a few lessons now. Today we're going to look at a formal definition of continuity. So, a function f is continuous at x equals a. So we're looking at one certain particular value, we can say whether a function is continuous at that value. If and only if, and this is called the three-part definition of continuity, so I'm going to give you three parts. So f is defined at a, which means that f of a exists. F of a has to exist. The second part is the limit as x approaches a of f of x exists. Okay? So the limit has to exist, which means that the limit as x approaches a from below of f of x equals the limit as x approaches a from above of f of x. So it has to exist around a, and it has to be approaching. There has to be a limit that's the same from both sides. And thirdly, they have to equal each other. The limit as x approaches a of f of x. So both of these things have to exist, and they have to be equal to each other. So the limit as x approaches a of f of x equals f of a. So in order to show that something is continuous, you have to show that f exists at a, find f of a, find the limit as x approaches a of f of x, and show that those two things are equal. Okay? So the idea of a continuous function is that it gets where it's going. Okay? And a function f is called continuous, so we call the whole function continuous if it is continuous for all a element of R or the domain of the function. So you can say some functions are continuous on certain domains, but they're not continuous everywhere. Okay? So we would call a function continuous if it is continuous at every point on which it exists. Okay? So we also, if we're looking at, so we've looked at things, we can use this definition for continuity across the whole domain or continuity on some kind of open interval if it's continuous for all a. If we're looking at a closed interval, how can we say a point is continuous? So we have two other definitions. So a function is continuous from the right at a, at x equals a, if the limit as x approaches a from above of f of x equals f of a. And similarly, a function is continuous from the left at x equals a if the limit as x approaches a from below of f of x equals f of a. So we're continuous from the right if the right-handed limit exists and is equal to the value of the function at that point, and we're continuous from the left if the left-handed limit exists and is equal to the value of the function at that point. Okay. First example. Okay. What kind of continuity does f of x have at x equals 3 if f of x equals 3x squared plus 1 for x less than or equal to 3, negative x for x greater than 3. Okay, so let's have a look. We're going to, in order to be able to figure out, we're going to check, let's first check f of 3, and then we're going to check if the limit of as x approaches 3 of f of x exists by checking the left hand and the right hand limits. So f of 3 is equal to, so for x less than or equal to 3, it's 3x squared plus 1. So f of 3 is equal to 3 times 3 squared plus 1. So that's 27 plus 1, which is 28, because the first function is operating at the exact point 3. Okay, so let's look at the limit as x approaches 3 from the left of f of x. Okay, this is equal to the limit as x approaches 3 from the left of 3x squared plus 1, because this is the function that is operating in our piecewise function before we get to 3 when we're to the left of 3. So this is going to be equal to something just below 3 squared. So 3 squared is 9, 28. So this also equals 28. And the last limit we have to check is we're going to look at the limit as x approaches 3 from above of f of x. So as we approach 3 from above, the other function, negative x, is operating. So this is the limit as x approaches 3 from above of negative x. So for any number that's bigger than 3, even if it's just slightly bigger than 3, that's our function. So we plug that in and we get this equals minus 3. Okay, so we can see this limit, because these two are different, the limit as x approaches 3 of f of x does not exist. And so that means that we are not, at 3, we are not a fully continuous function. However, because f of 3 is equal to the left-handed limit, we can say the function is, okay, so therefore here the function is not continuous. Not continuous at x equals 3. But because these two are the same, we can say the function f of x is continuous from the left at x equals 3. So it's sort of partially continuous, and the continuity is coming from the left. We can also define, so we've defined continuity at a point, and we've defined sort of different kinds of continuity at a point. So it can be fully continuous, or it can have continuity from just one side, or it can be not continuous at all. So we have one more definition, which is we can define continuity on an interval. And we're going to define it on a closed interval. A function f is continuous on an interval ab, and this is a closed interval where we're including the endpoints, if it is continuous on the open interval ab. So every point on the open interval, not including the two endpoints, it has to be continuous at those points. Continuous from the right at A, so at the starting endpoint. At A, and continuous from the left at B. Because on those endpoints, it's not going to be able to be continuous from both sides, because the function, we're looking only at that closed interval. So we're not considering points that are outside of that closed interval. This is continuous from the left at B. So let's see how we could show this level of continuity. And generally, when you're proving that something is continuous, you need to prove that we are continuous on the end point. So on the interval, we're looking to prove that it's continuous in the middle, and then also continuous from the right on one end point and continuous from the left on the other end point. Okay? So the first one, to prove that we are going to, so let's set up our function. I think I skipped a line in my notes there. So we're going to show that the function f of x equals 1 minus radical 4 minus x squared is continuous on the interval -2, 2. And we're looking on the closed interval here. Okay, so first thing we're going to do is we're going to show that it's continuous on the open interval, so that for all points between -2 and 2, it is continuous. Okay, so let's see, we have for a between -2 and 2, the limit as x approaches a of 1 minus radical 4 minus x squared, and that is equal to 1 minus radical 4 minus a squared. And so the key thing here is that this stuff under here is always going to be greater than or equal to, it's actually always going to be strictly greater than 0. Okay, because a has to be between -2 and +2. So anything between -2 and +2, when you square it, is going to be smaller than 4. So because this is always going to be greater than 0, we know that this is going to be just equal to f of a, which proves that this is continuous. We know that this limit exists because it's always going to be greater than 0. There's no funny business happening with indeterminacy or anything like that. And we know that it's equal to the function. So we are, therefore, f of x is continuous on the open interval -2, 2. Okay. So second part, we're going to prove that what happens when x approaches -2 plus of 1 minus radical 4 minus x squared. Okay, this is equal to 1 minus radical 4 times -2 plus squared, so something that's just slightly larger than -2. 4 minus -2 plus. So when we square something that's slightly smaller than -2, we get something slightly larger, slightly smaller than 4. So this is going to be equal to 1 minus radical 0 plus. And it's really important when we have something under a radical that we're only looking at 0 from above, because if we get a 0 from below, that's not going to exist there. Okay, so this is equal to f of -2. Which is 1. So that means f of x is continuous from the right at x equals -2. So we're continuous from the right at x equals -2. And lastly, the limit as x approaches -2 from below. Oh, sorry, +2 from below, not -2 from below. That's the other end of our interval. We're still taking the limit of the same function, 4 minus x squared, radical 4 minus x squared. So this is equal to 1 minus radical 4 minus 2 minus squared. So something just slightly smaller than 2 squared. As we can see, this is going to be equal to 1 minus radical something just slightly bigger than 0, which is cool. As long as it's slightly bigger than 0, we're okay. So this is equal to f at 2. So we are fine with this. Okay, so because of this, f of x is continuous from the left at x equals 2. And because of all three things, we're continuous on the open interval, we're continuous from the right on the left-hand endpoint, and we're continuous from the left on the right-hand endpoint. So by 1, 2, and 3, f of x is continuous on the closed interval, -2 and 2. And now a lot of this may seem like, oh, you're just proving it's pretty obvious, but you do need to actually go through and state each of these steps. You want to show that you're understanding what the definition is, and you're showing that this function meets this particular definition of continuity and avoids any discontinuities in those places. Okay, so a couple of theorems that can help you prove that certain functions are continuous. Number 1, any polynomial function p of x is continuous on R. So for all real numbers, p of x is continuous. Okay? Any rational function p of x over q of x, where p and q are polynomials, is continuous for all x where q of x is not equal to 0. So wherever it is defined, the function is continuous wherever it exists. Okay, so they're just the only discontinuities would be where q of x is equal to 0. And number 3, a function of the form the nth root of x equals f of x is continuous on the following intervals: 0, positive infinity, if n is a positive even integer, and on negative infinity, infinity, if n is a positive odd integer. Okay, and most functions that we deal with are continuous. Absolute value functions, if you have a bunch of linear absolute value or quadratic absolute value functions, those functions are all continuous. They do some funny bending, and as we get into our next chapter, we're going to see that there is something that's not going to work out quite so well at the point where they bend, if you have like a sharp corner or something. But a sharp corner, as long as the function exists and the limits coming from both sides are equal to each other and equal to the value of the function at that point, the function is continuous. Think of it as taking your pencil. Continuity is like taking your pencil and drawing. If you have to stop and lift your pencil, then the function isn't continuous. If there's any jumps or a little place where you have to pick up your pencil just for a second and draw a hole, then it's not continuous. If you can draw it smoothly without lifting your pencil at all, that's continuous.